Welcome to Lesson 3. In the last two lessons, we treated protons and neutrons as the fundamental bits of the nucleus, but they're not fundamental at all. Today we meet the true building blocks, quarks and leptons, and we'll learn the conservation laws that decide whether any given interaction is even allowed to happen. Here's the plan for today. Let's start with quarks. The big, heavy particles, protons and neutrons, are each made of 3 quarks, with each quark carrying roughly a third of the overall properties, like mass and charge. At A level, you need 3 quarks by name, up, down and strange, and each of those has an anti-quark partner, which we write with a little bar on the top. Here are the numbers that you have to know. Up has charge plus 2/3, down and strange both have minus 1/3. All 3 quarks have a baryon, which we can think of as being like the mass number of plus 1/3. And strangeness is the odd one out. It's 0 for up and down quarks, but minus 1 for a strange quark. For any anti-quark, you simply flip the sign of every value, including the mass. We can use this to see which quarks make a proton or a neutron. A proton has charge +1 and baryon number +1. So from the combination of the quarks, we can see that the answer is up, up, down. A neutron with charge 0 is up, down, down. Antiproton and antineutron, just put a bar over every quark. And notice what beta decay looks like down here. Turning a proton into a neutron actually just flips a single quark and up into a down or a down into an up. Particles built from quarks come in 2 families. Baryons are made of 3 quarks. Protons and neutrons are both examples of baryons. Mesons are the other family, a quark-antiquark pair. Because you've got a quark and an antiquark together, their baryon numbers cancel, so every meson has baryon number 0. The main examples are pions and kaons, and they carry charge +1, 0, or -1, depending on which quarks are inside. We can see that we can construct a meson tree of all the different combinations of quark-antiquark pairs. Just to lock in that baryon number rule, it's +1 for a baryon, -1 for an antibaryon, and 0 for everything else, mesons included. Then there are leptons, and these really are fundamental. They aren't made of anything smaller, they are just themselves. The ones that you need to know are the electron, the muon, which is like a heavy electron, about 200 times the mass, and the neutrino. Each has a corresponding antiparticle too. Leptons get their own conservation number, called the lepton number. +1 for a lepton, -1 for an antilepton, and 0 for anything that isn't a lepton. Keep that separate in your head from the baryon number, as they're counted independently. Let's put the whole particle zoo into one picture. All matter divides into 2 groups, hadrons, which are quark-based particles, and leptons, which aren't. Hadrons then split again into baryons, which are 3 quarks, and mesons, a quark and an antiquark. A really important feature of the baryons is that the proton is the only stable baryon, which means over time all baryons decay to become a proton. Here's the heart of the topic, the conservation laws. In any interaction, you need to make sure that the totals on the left-hand side and the right-hand side are the same. Energy and momentum are always conserved, as are charge, baryon number, and lepton number. Strangeness is a sneaky one. It's conserved in the strong interaction, but in a weak interaction, it's allowed to change by 0, +1, or -1. So if an exam question shows strangeness changing by 2, that reaction is definitely wrong. It can't happen. Write every interaction out as a balanced equation and remember that a +1 and a -1 can cancel to 0, which is how we can have hadrons appearing on only one side of the equation. Finally, a quick guide to which force is responsible for what. Gravity is negligible at the particle scale, so we ignore it. Electromagnetism acts between charged particles. The strong force acts on anything made of quarks, so baryons and mesons, but never leptons. And the weak force is the force of change. Whenever something decays or transforms into something else, that's the weak interaction at work. And leptons can only ever interact via the weak force or electromagnetism, never the strong. That's it for today's video. Next time we switch from the nucleus to light itself with one of the most important experiments in physics, the photoelectric effect. Thanks for watching, and check out my tutoring page in the description.